These are the Gaussian primes, and these are the Eisenstein primes. They're both sets of complex prime numbers, but they're not alone. Here are some other ways that we can apply the idea of primes to the complex numbers. I made a website that lets you explore these. It's linked in the description. And in this video, I'm going to talk about how we apply the idea of primes and some cases where it goes wrong, where we get numbers that are kind of prime, but kind of not. And we can make these primes using the quadratic integers. These are numbers of the form a plus b root d, where a and b are integers and d is a fixed integer. But this isn't quite correct. We'll clarify that later. And going forward, I'll denote this as o root d. And maybe the simplest example is o root negative 1. So these are the numbers a plus b root negative 1. But we typically write root negative 1 as I. This is a plus b I. And these may look familiar. They are the Gaussian integers. And I made a previous video about the Gaussian integers and how we can find Gaussian primes, which are displayed here in color. And we find Gaussian primes similarly to how we find the natural primes. We often use the definition that a prime number is only divisible by 1 and itself. And maybe we can think of this instead as a prime number has the minimum amount of divisors. Everything is divisible by 1, everything is divisible by itself, so primes have the bare minimum. And we're ignoring 1, that's a special case. In the Gaussian integers, the minimum is higher. Every number is divisible by 1, negative 1, I, and negative I. We call these the units. They divide everything. Every Gaussian integer z is also divisible by z, zi, and negative zi. This is z times each of the units. And we call these the associates of z. So we can define a prime as having the minimum divisors. They only have these 8 divisors. Using this definition, 3 is a Gaussian prime. These are all of the factors of 3. It has the bare minimum 8 factors. But 2 is not a Gaussian prime. 2 has its bare minimum 8 factors, the units and the associates, but it also has these 4 extra factors. So it is not prime. The prime factorization for 2 is 1 plus I times 1 minus I. And every Gaussian integer similarly has a prime factorization. For example, here is the prime factorization of 17 plus 9i. Now, we also have this prime factorization and this prime factorization, so it's not strictly unique, but all of the yellow numbers are associates of each other. They're just a unit away. And the same is true for the red and the purple. So we can get unique factorization if we consider associates to be equivalent. And this generally doesn't create any problems. So we do get a kind of unique factorization. Now let's take a look at o root negative 4. These are the numbers of the form a plus b root negative 4. But we could write that instead as root 4 root negative 1, which we could also write as just 2i. So these are all the Gaussian integers with an even imaginary coefficient. Visually, here we have all of the Gaussian integers. What we're doing with o root negative 4 is just removing every other row. We're removing all of the odd rows. In the Gaussian integers, every number had these 8 factors, but I and negative I are not in o root negative 4. They have an odd imaginary coefficient, and that means that these two numbers are no longer associates of z. So in o root negative 4, our minimum divisors is 4, the units 1 and negative 1, and the associates z and negative z. Now we see that 3 is a prime in o root negative 4. It was a Gaussian prime and it remains a prime. These were its factors. We no longer have I or negative I, and we no longer have 3i or negative 3i. So it still has the minimum. 2 is also a prime in o root negative 4. It wasn't a Gaussian prime, but it becomes a prime. These were all of its factors. It had 4 extra. But we notice those 4 at the bottom all have odd imaginary coefficients, so they're not in O root negative 4. We also lose I and negative I, and therefore 2i and negative 2i are not associates of 2. So 2 has just the minimum 4 divisors, and it's prime. Now we want to notice that 2i and negative 2i are still in O root negative 4. They have even imaginary coefficients. They just aren't associates of 2 because we lost those 2 units. And in fact, these 4 numbers are all prime in O root negative 4. But in the Gaussian integers, they were all associates. They were a set of 4 associates. In O root negative 4, that's been split. We have the 2 associates 2 and negative 2, and then the associates 2i and negative 2i. And this is where we run into a problem. Let's say we want to find the prime factorization of 4. Well, 4 is 2 times 2, but 4 is also 2i times negative 2i. And 2 is not an associate of either 2i or negative 2i, so these are 2 different prime factorizations. 4 does not have a unique prime factorization, so maybe it'd be better to call these the prime factorizations of 4. And so these numbers are bad at being prime. One of the reasons we like to use primes is because they give us a unique factorization, but we just saw that fails with these values. So what happened? Let's go back to our definition. We said a prime number has the minimum amount of divisors, but this gave us some primes that didn't really work that well. In my previous video, I introduced an alternative definition. If P is prime, whenever P divides AB, then P divides A or B. Let's think about this definition for the natural numbers. If P is prime and P divides AB, then P will appear in the unique factorization of AB, which means that P has to appear in either the unique factorization of A or B, so it'll divide A or B. On the other hand, if we have a composite number C, then we could write C as the product of 2 smaller numbers A, B, and C definitely can't divide A or B if they're smaller. And this is not just an alternative definition in the natural numbers, but also the Gaussian and the Eisenstein integers. Now let's see how we apply this in O root negative 4. So 2 divides 4, which equals 2i times negative 2i, but 2 does not divide either 2i or negative 2i, because we don't have I or negative I in O root negative 4. But that means that 2 fails this alternative definition of a prime. So maybe we should say that 2 is not prime in O root negative 4. But it did hold for our first definition, having the minimum amount of divisors. So maybe we should say that 2 is prime in O root negative 4. And now we're noticing these 2 definitions aren't the same, so they can't both define a prime number. The definition on the left is our typical definition for a prime number. The definition on the right defines what is called an irreducible. An irreducible number has the minimum amount of divisors. It's only divisible by units and its associates. We can't reduce it into anything else. So 2 is irreducible in O root negative 4, but it's not prime. There is a link between these numbers, primes and irreducibles. Every prime is an irreducible. Using the definition of a prime, we also get the property that they're minimally divisible. But we can't necessarily say that every irreducible is a prime. It doesn't go the other way. The definition of a prime is more strict. But all the irreducibles were prime in the natural numbers and the Gaussian and Eisenstein integers, and that's because they are equivalent when we're working in a Euclidean domain. And by that we mean a domain where we can use the Euclidean algorithm to find greatest common divisors. So if we can find greatest common divisors, we'll assume we have some irreducible P that divides AB, and then we find G to be the greatest common divisor of P and A. Because P is irreducible, and G is a divisor, that means either G is an associate of P, and G divides A, which means P divides A, or G is a unit, which implies that P and A are coprime, so we can write 1 as P times some x plus A times some y. Now, we can multiply this equation all by B, and we see the right side is divisible by P because P divides AB, which means the left side must also be divisible by P, so B is divisible by P. So either P divides A or P divides B, which means P is a prime. Irreducibles are prime if we can find greatest common divisors. So the Euclidean algorithm gives us irreducibles equal to primes, which gives us unique factorization. But what is the Euclidean algorithm? Let's say we want to find the greatest common divisor of 150 and 66. We'll start by dividing 150 by 66, and we get 2 with a remainder of 18. So we'll write that as 150 equals 66 times 2 plus 18. Now we divide 66 by 18, and we get 3 with a remainder of 12. So we write that. 66 is 18 times 3 plus 12. And now we repeat with 18 divided by 12, and then we rewrite that. And in our last step, 12 is just 6 times 2. And now we have a remainder of 0. 12 is evenly divisible by 6, which means that 6 is our greatest common divisor. Now we can verify this if we want to look at the prime factorization of 150 and 66, and we see they share the primes 2 and 3. And 2 times 3 is 6. 6 is the greatest common divisor. Now in the Euclidean algorithm, at each step we take the divisor and it becomes the dividend of the next step. And then the remainder becomes the divisor of the next step. And we can use this not just with the natural numbers, but also with the Gaussian integers. So if we want to find the greatest common divisor of negative 26 plus 26i and 15 plus 10i, we can repeat the same process. And these are what the steps look like. And we end up with a remainder of 0, showing us that 3 plus 2i is the greatest common divisor. And again, we can look at the unique factorizations and see that 3 plus 2i is the only prime that divides both numbers. So it's sensible that that's the greatest common divisor. Now let's try to apply this to O root negative 4. What's the greatest common divisor of 4 and 4i? Well, we have 4 equals 4i times 0 plus 4. And then 4i equals 4 times 0 plus 4i. And the next step is just identical to the first row. And so here we've entered an endless loop. And all the programmers will know that is something we want to avoid. It's very important that the Euclidean algorithm eventually stops. That works with the natural numbers because our remainders always get smaller. In this example, we had 8, and then 12, and then 6, and then 0. And that's because every divisor gives us a remainder that is less than itself. That remainder becomes the next divisor, which gives us an even smaller remainder. And this is because in the natural numbers, dividing by n gives us a remainder r, such that r is non-negative but less than n. So we have a sequence of decreasing non-negative integers, which means we'll eventually get to 0. And so I like to think about this as every integer k is within n of a multiple of n. So dividing by n gives us a remainder that's less than n. And we can visually see this if we have a number line. We highlight all of the multiples of 2. If we put circles of size 2 around them, we cover every number. And we can do the same thing with the multiples of 3, and the multiples of 4, and the multiples of any number. We will cover every integer. We can do the same thing with the Gaussian integers. So here we highlight all of the multiples of 2, and then if we give each a circle of size 2, we see every Gaussian integer is covered. Everything is within 2 of a multiple of 2. And we can do the same thing with the multiples of 3, give them all a circle size 3, and everything is covered. The same thing with the multiples of 4 and any other Gaussian integer. So the Gaussian integers are Euclidean. Now, we recall the Gaussian integers are O root negative 1. But what about O root negative 2? Here the rows are spread a little bit further apart. But this still works. So here we highlight all the multiples of 2 and give each a circle, and we see that all of the integers are covered. And so this gives us another way of making complex primes. O root negative 2, and this is what that looks like. Now let's look at O root negative 4. The rows are even further spread out. And if we highlight all of the multiples of 2 and give them each circles, we see the integers are no longer covered. All of these points in yellow are outside of the circles. They are not within 2 of a multiple of 2. So there are some cases where the Euclidean algorithm fails. And this is why we don't get unique factorization in O root negative 4. But you may notice I skipped from O root negative 2 to O root negative 4. What about O root negative 3? That's between them. Here the numbers aren't quite so spread out. Well, let's highlight all of the multiples of 2, give them each a circle, and it appears that everything's covered, but all of these yellow points are on the circles. They're not within a circle. So they're not within 2 of a multiple of 2, they're exactly 2 from a multiple of 2. And that doesn't work nicely with the Euclidean algorithm. However, this isn't actually O root negative 3. O root negative 3 has a lot more points. We have these extra points that are between the rows. And this gives us kind of a triangular or a hexagonal grid. And you may remember a triangular grid from the previous video. These are actually the Eisenstein integers. O root 3 is the Eisenstein integers, and we get the Eisenstein primes from them. So now, if we highlight every multiple of 2 and give them all circles, everything is covered, and the Eisenstein primes are Euclidean. So O root negative 3 is defined actually a little bit differently. It's all of the numbers a plus b root 3, where a and b are integers, but also a over 2 plus b over 2 root 3, where a and b are odd integers. This second set of numbers are those points in between the main lines that are shifted. So why is O root 3 defined differently? These aren't really integers, they are halves. But the norm of these are integers. For example, the norm of a half plus a half root 3 is 1, whereas the norm of a half plus a half I is 1/2. So maybe we can think of the integers root negative 3 as not having integer coefficients, but having integer norms. But this isn't exactly true. A more precise way to define them is the roots of an equation x squared plus bx plus c. So half plus half root 3 is a root of x squared minus x plus 1, whereas a half plus a half I is a root of 2x squared minus 2x plus 1. We notice that the leading coefficient of the second value is a 2. And there are some cases where we only want to work with leading coefficients 1. So it's natural to define the roots of equations with leading coefficients 1. But we don't have time to get further into that. So here we are back with the definition of O root negative 3, but this also applies to O root negative d for any d that's 1 mod 4. And these are most naturally displayed hexagonally. So here are some other examples where d is 1 mod 4. Here is 5, and -7, 13, and 101. And instead of that previous definition, it's standard to define these as a plus b omega, where a and b are integers and omega is 1 plus root d all over 2. And so now we can adjust the definition of all quadratic integers, O root d, to be a plus b omega, where a and b are integers. Omega is 1 plus root d over 2 if d is 1 mod 4, and omega is just root d otherwise. And then d is a fixed integer. Although we still have an asterisk here that we need to clarify. O root negative 4 did not have a unique factorization. And these values were a plus b root negative 4, but you recall we could just write that as a plus b 2i. So these were a subset of the Gaussian integers. And that gave us some problems just working with a subset of quadratic integers. And similarly, if we have any O root d, with d being divisible by a square, that means that d is equal to some c squared times little d, then a plus b root d could just be written as a plus b root c squared d, which is just bc root d. So this is also going to be a subset of some other quadratic integers, and we will run into similar problems. And because of this, we restrict d to being a fixed square-free integer, meaning that it is not divisible by any squares. So O root -4 aren't really quadratic integers. I use them for example, but they don't really fit with the typical definition. Now that we've cleared up this definition, let's actually find the primes. Previously, I showed how we can find the Gaussian and Eisenstein primes using a sieve method. And we could do the same thing for any quadratic integers where d is negative. We call these the complex quadratic integers because we're taking the square root of a negative number. So for O root -2, we start with everything but the units, and we find the smallest numbers, and then their prime, and we remove their multiples. And then we find the next smallest numbers, and we continue this process until we're left with just the primes. But instead of using a circle, we're using an ellipse because I squished the axes to make a square grid so we can see more data. We can also do this with O root -7. These quadratic integers also have unique factorization. And -7 is 1 mod 4, so it's hexagonal. And the same applies to O root -11. These four start out identical. Their primes give them the same pattern, and they slowly start to diverge, but even at the end of the process, the vicinity around 0 looks the same. And these four are an interesting case. They have unique factorization, but they're not Euclidean. Being Euclidean is sufficient for unique factorization, but it's not necessary. There's a wider group of domains called unique factorization domains that contains all of the Euclidean domains, but also some others. But there's not many complex quadratic integers here. These 9 that we've looked at are the only complex quadratic integers that have unique factorization. Everything else fails. We get some more with the real quadratic integers, where d is positive, but they're a little harder to deal with, so we'll expand on them in my next video. To wrap things up, I've had some comments request a wider view of these primes, so I updated my website to allow an option for zooming out. This option does disable some of the other features to keep the site running smoothly, but it's enough to get a general view. And with that, thanks for watching, and I'll see you soon with the final video in this series.